Hi again, Mr. Nichols here, and today I'd like to talk about how you work with velocity time graphs to determine things like average acceleration, displacement, distance traveled. So we have in front of us here an example of a velocity time graph. We have 5 different sections of motion here. We have one section from 0 to 10, where one type of motion is happening. We have a change from 10 to 16, and 16 to 20, same motion. 20 to 28 is another motion. Oh, sorry, 20 to 30 is another motion. And then 30 to 32. So we're going to have different segments we may be looking at here. We're going to lead off right with one of the first equation-based calculations here, which is the average acceleration. And we're going to look at what happens between 20 and 30 seconds. And so first thing you're going to do is you're going to write down the equation. The acceleration is your change in velocity divided by your change in time. And what that's going to mean is this actually means the final velocity minus your initial. So what is the velocity with which we're starting the analysis and where are we ending? And then what is your time span? What time do we finish at? What time do we initially start at? So being very careful to read this. Okay, I intentionally put this curve so you have to read in between the grid. So this would be negative. If this one is negative 10, the next one's negative 20, we're going to be negative 15 meters per second is my final velocity. Minus an initial is 60 meters per second. And we're going to divide that by the time span of 30 seconds to 20 seconds. Now if we look at the math on this, what ends up happening is this. I'll reduce that a little bit so I get a little more working space here. So this is going to end up being negative 75 meters per second over 10 seconds. So the average acceleration, now watch the units here, negative 7.5. Now this is a meter per second squared because you have a meter per second divided by a second. That is the correct unit for acceleration. We are moving from a positive velocity to a negative velocity, so we're going to have a negative acceleration rate. That's how you do the first one. You would follow the same process if I asked you for what was going on between 0 and 10, initial velocity, final velocity. If I asked you between 10 and 20, initial velocity, final velocity. So it's a fairly straightforward procedure. The more challenging aspect is why we're making these shapes to calculate displacement. It's a technique I talk about in class, but there are certain graphs where if you multiply the value on the y-axis by the value on the x-axis, the units, you end up with a unit that is recognized in physics as being an actual quantity. In this case, if we take a velocity and multiply it by a time, we get a length. And so the area, calculating or shading the area between the graph and the time axis gives us the value of the displacement. Let me show you what I mean. If you're asked to calculate the object's displacement from 0 to 20, first thing I want to do is kind of mark where I'm at. I'm going to start here and I'm going to here. Now the way I describe this is when you decide what you're shading in, the shading is done when you look at trapping the shape in between where the graph is, the red line, and the time axis, which is here. Therefore, if you're going to shade this, the area that you're shading, you're going to make this into a triangle. That's my first shape. So notice, the red line was below the axis. I filled up. Now the next segment, we only want to go to 0 to 20. So we're going to basically effectively say we're only looking here, so I can close my shape or drop a line there, and now I have a trapezoid. If you don't know how to do the area of a trapezoid, we got to break this up into similar, smaller shapes, easier shapes. So we're going to have a triangle here, and then a rectangle. We're going to ignore everything else. So technically we're shading this whole area in here. Notice what I did. The function, the line is right there in red. We have to trap the shape in between that and the time axis. So you have to fill in between those two. And that's why I shaded where I did. Notice the pattern. When the function is above the time axis, I fill down. When the graph of the function is below the time axis, I fill up. So you're always filling in between the spaces. The shape always touches the time axis. Well, if we're going to break this thing up, I'm going to need some extra space here. So let me get rid of all this so I can have some working room here. If I look at this as being specific areas, I typically break these up into areas and say, well, this is the area of shape 1. This will be the area of shape 2. And this will be the area of shape 3. Now, the area isn't an actual area. It's a technique for arriving at a value. That value represents the displacement of that object. So if I'm shading this, and again, I want to figure out the value. The area of shape 1 is a triangle, which is 1/2 base times height. Now this isn't an actual triangle, it's a graphical triangle. So be mindful of the units here. The base is always units of time. So the base is 10 seconds wide. Notice the height though. We have a negative height because velocity can be positive or negative. It just means moving to the left or moving to the right. So the height of this is a negative 50 meters per second. And when you do the math on this, what you're going to see is that if you multiply these together, you're going to get 250. Now notice what happens. We have a meter per second times a second. So the seconds are going to cancel, and it's going to leave us with just meters, which is the correct unit for a length. So this object will travel 250 meters in the first section. Now it's going to be negative. So it has moved to the left for 250 meters. If we look at the second shape, so move that right there for now. So second shape, area 2. This is also a triangle. And we have a base that is, now be careful here, don't count blocks. I'm going to be very, very emphatic about that. Look at the units there. 3 blocks, each block is 2 seconds long. You have 6 seconds of length in the base. The height, 60 meters per second. We're going to end up with 180 meters traveled for area 2. And now the final one, area 3. That is just a rectangle, so base times height. The base is 4 seconds long, and the height is still 60 meters per second tall. This produces a length or displacement of 240 meters. So let's see if that makes sense. We have 6 by 60, 360, 180, and we're 4 by 240. So what has happened here is the displacement is going to be adding up all those values, knowing that the negatives are to the left and the positives to the right. So these are going to work against each other. So if you sum these values up, so the total displacement is made up of 3 individual subsections, and so we have a minus 250, a plus 180, and a plus 240. And that will be the total displacement of this entire situation. Now, here's how I view it. The 250 and the 240 are really close. So 240 of that negative is going to cancel out with this. So you're going to end up netting a negative 10 here. You have 10 units left over. And so you're going to end up, in the end, with 170 meters displacement. If you don't trust me, do the math. You'll see how it works. That's how you get displacement. The last aspect to this is if I asked you for the distance traveled. So the object's displacement, 170 meters. Here's your final answer there. Distance traveled, this is going to be a quick one here. Remember, distance is the absolute value of the displacements, of all the individual displacements. So if you look at the values you had, everything's effectively done here. We go back up. Okay, we had a negative 250, which we don't care about the negative anymore. And then we had 240, positive. And we had 170, all positive. So you're just going to sum those numbers up, disregarding any of the positives or negatives. So you got a 250. I'm going to add that to 240, which gives us 490. And then finally, it should be 660. So the total amount traveled, regardless of left or right, is 660 meters. This gives you a very quick glance as to using a VT graph, the equations you will use to calculate average acceleration, the equations you will use to calculate the displacement using the approximation of areas, and then determining distance using the individual segment displacement values. That's all for now. Thanks and take care.